Hi, this is Sonia Doucette. In this video, I'm going to show you how to find the binding energy per nucleon for a nuclide. And this is useful because it can help you understand how stable one nuclide is relative to another. This problem says to calculate the binding energy per nucleon for potassium-40, and you're given the mass of that potassium-40 nuclide there. So remember, a nucleon refers to both protons and neutrons. So nucleons are both of those. So what you want to do to approach this problem is you want to find the energy in mega electron volts per nucleon. And to figure that out, you first need to know the nuclear equation for the formation of a nuclide from its component particles. So component particles just mean what the nuclide is made up of. And you all know by now that nuclides are made up of protons, neutrons, and electrons, just like all other atoms. So protons are represented, and electrons are represented by a hydrogen with a Z value of 1 and an atomic number of 1. So what this is representing is a proton, and because it has a neutral charge, you can assume there's also an electron there too, because if it didn't have an electron and just a proton, it would have a positive charge. So that is how a proton and electron are represented. Then you also have to include the neutrons. So they're represented like that. So you're saying that protons and electrons plus neutrons will give you your potassium-40 nuclide or isotope. So what you need to do is you need to figure out the number of protons and electrons, which is your first term there, and the number of neutrons you need to get potassium-40. So you can look at those and say, well, I'm going to put the number for this 19 in front of the proton and electron representation, because 19 times 1 is going to give you 19. And for neutrons you have 0, so you multiply anything by 0, it's going to give you 0. So you have to use the 19 for a coefficient in front of that first reactant. And then you just make up the difference for the coefficient of the neutrons. So on the top, you're still saying 19 times 1 is 19. So what you want to do is say 40 minus 19 is what? Well, it's 21. So 21 times 1 plus 19 times 1 is going to give you 40. So you've accounted for all the neutrons and all the protons. So now you have your equation. The next thing you want to do is you want to find what's called the mass defect. So that's the difference between the mass of the component particles, which are your two reactants in this equation, and minus the mass of the formed nuclide, which in this case is the potassium-40. So let's write that out. You have your potassium-40 mass defect being equal to the mass of component particles, and again that is all your protons, neutrons, and electrons, so I'm just going to say reactants, referring to the equation above, minus the mass of your formed nuclide. So formed just means that's what you have after all of those protons, neutrons, and electrons in the reactants get together to form the atom. So next, to find the mass of the component particles, you say you have 19 times the mass of the protons and electrons, that's in atomic mass units, plus 21 times the mass of a neutron, so you have 21 neutrons, and then you subtract the mass of the nuclide, which you're given. It's 39.96400. So when you do the math there, what you end up getting is 0.366663 AMU. And you want to convert atomic mass units to mega electron volts. So a useful conversion there is that there are 931.5 mega electron volts in 1 AMU. So you're going to get from that 341.52 mega electron volts. And then finally, you want to know the binding energy per nucleon. So remember, nucleons are going to be your protons plus your neutrons. It's those particles that make up the nucleus, as opposed to the electrons, which are outside the nucleus. So potassium-40 has 40 nucleons. You know that this number means protons plus neutrons. So you're just going to divide that 341.52 number by 40 nucleons. And what you'll get there is 8.5379 mega electron volts per nucleon. So this is the binding energy. So the greater the binding energy, that means it's harder to pull apart those neutrons and protons from each other. So the greater the binding energy, the lower the potential energy, and the more stable the nuclide is. So you could calculate the binding energy per nucleon for two different nuclides, and you could tell which one is more stable by comparing their numbers.